Okay, so yeah, uh, good evening, everybody. I mean, good afternoon, and as usual, I don't think anybody will join today also. So I'll upload this video on the YouTube for the help for the 12th week assignment, and also for the final exam. Your exam is near. I think it is on 20th. So yeah, so this is a combined video for the week 11th and week 12th classes, and first of all I will as usual go through the matters being taught by Professor Mahapatra, and after that I'll discuss the assignment of class 11th and 12th. So let's go to directly to the discussion. So yeah, let's see, these are the short notes just for giving you a flashback. We are studying actinide chemistry. So if we talk about actinide chemistry, the definition is that the elements in which the extra electron enters the 5f orbitals of n-2th mean shell are known as 5f block elements, and they are known as actinides or actinodes. Thus, according to the definition of actinides, only 13 elements from TH95F06D to 7s2 to NO102, which is 5F146D07s2, should be the members of actinide series. However, all the 15 elements from AC89 5F06D17 7s2 to LW103 are considered as the members of actinide series, since all these 15 elements have same physical and chemical properties. In fact, actinium is prototype of actinides, as lanthanum is a prototype of lanthanides. So the general electronic configuration of actinides is 281832, 5s2 p6d10, f0 to 14 6s2 p6d02 2 and 7s2. So the electronic configuration of the actinides is, for actinium it is 5s0 6d1 7s2, thorium 6d2 7s2, and then protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, actinium, fermium, mendelevium, novalium, and lawrencium. And these are the oxidation states of actinide elements. As we can see, for actinium it is generally +3, thorium +4, Pa +4 +5, U shows from +3 to +6, neptunium shows from I think +3 to +7. Similarly, plutonium, americium, and curium, berkelium, and then californium, and then einsteinium, and all these later on till lawrencium shows mainly +3 states. So the oxidation state becomes increasingly more stable as the atomic number increases in the actinide series. The increasing stability of the +3 oxidation state is illustrated by the increasing difficulty of oxidation above +3 oxidation state. Actinides show a greater multiplicity of oxidation states, since in the first half of the actinide series, the energy required for the conversion of 5f to 6d is less than the required for the conversion of 4f to 5d. Lower actinides should show higher oxidation states such as +4, +5, +6, and +7. Correspondingly, since in the second half of the actinide series, that of higher actinides, the energy required for the conversion 5f to 6d is more than that of required for the conversion 4f to 5d, and the higher actinides should show more lower oxidation states such as +2. So the tripositive oxidation state occurs widely in each series. For thorium and Pa, it is +4 and +5. The different oxidation states are explained as under. +2 oxidation state is only Am. It is known to form a stable +2 state. +3 is most of the actinides. For Th and Pa, it is +4 and +5. +4 oxidation state, this is a principal oxidation state. For thorium, and is a stable oxidation state up to Am. Am +4 and Cm +4 exist only as complexes in concentrated fluoride solution of low acidity. General chemistry of An+4 ions is similar to that of Ln+4 ions. The hydrated fluorides and phosphates of both An+4 and Ln+4 ions are insoluble. So THO2, PaO2, and all these elements, and then +5, +6, and +7. Similar to lanthanide contraction, there is actinide contraction. The shielding of one f electron by another from the effect of nuclear charge is quite weak on account of the shape of the f orbital. Hence, with increasing atomic number, the effective nuclear charge experienced by each 5f electron increases. This causes shrinkage in the radius of atoms or ions as one proceeds from AC to LW. This accumulation of successive shrinkage is called actinide contraction. Okay, so this is the difference in a table of lanthanides and actinides. In lanthanides, a newly added electron enters in 4f orbitals. In actinides, a newly added electron enters in 5f orbitals. The name lanthanide is given because the first element is lanthanum and all the other elements have similar property to that of the lanthanum element. The name actinide is just given because the first element is actinium and all the other elements have similar property to that of actinium element. They have less binding energy, hence less shielding effect in 4f orbital. They have more binding energy, hence more shielding effect in 5f orbital. They have low tendency to form complex. They have greater tendency. Their color absorptive spectra are less intense than actinides. Their color absorptive spectra are more intense. They have lower ionic radii. They have higher ionic radii. They have more magnetic moment. They have less magnetic moment. So the position of actinides in a periodic table is can be explained in two ways. It is prior to the discovery of transuranium elements and then following by the discovery of the transuranium elements. Now separation of actinized elements, it can be done in many methods. The first one is solvent extraction, as we have really read it. Because of the high velocity and density, TBP is used, which is tri and butyl phosphate or a dithilateral. This method is preferentially applied to a nitrate system. And this is a chart where this CO2 2 positive Pu plus 4 is oxidized by K2Cr2O7, and then AlNO3 whole tries and extract with hexane. Then there is aqueous phase and then there is the organic solvent phase. Then this is washed with aqueous SO2. Organic solvent phase is there, aqueous phase is there, then repeat oxidation extraction cycle. Now separation of Pu and U from fission products by solvent extraction with tributyl phosphate TBP. It is a Purex process. Extract with TBP, aqueous phase. Organic solvent phase, UO2 plus 2 plus Pu4 plus. Treat with SO2 or NH2OH. Organic solvent phase, aqueous phase, and then oxidize. So the ion exchange technique, which is this is the best technique to separate the actinide ion. This method involves the following two steps: lanthanide actinide separation. The actinides as a group are separated from lanthanides by cation exchange resin. Strong HCl is used as a eluting agent. The actinide ions from chloride complexes more easily and hence are eluted first. Then there is separation of individual actinide elements. The actinide ions can be separated from each other by removing from the cation exchange resin by elution from ammonium citrate, lactate, alpha hydrogen isobutyrate, and ethylene diamine tetraacetate. If the activity is plotted against a number of globs of eluent, elevation curve will be obtained as shown below. Then comes about elution curve for the elution position of Ln3 and An3 positive. So color and absorption spectra of the actinide ions can be seen here. For An3 positive, it is colorless, TH An4 positive, and then comes uranium, neptunium, then americium, and then these all elements are there. Then there is a concept of this magnetic moment. Magnetic properties of actinide elements for Pu3 plus Am3 plus. These ions show analogous behavior as noted from Sm3 plus and U3 plus ions in 4f series. The magnetic properties of the actinide ions are considerably more difficult to explain than those of the lanthanide ions. The values of magnetic moments found experimentally are usually lower than those calculated using Russell-Saunders coupling scheme. This is due perhaps to the inadequacy of the Russell-Saunders coupling scheme for 5Fn ions and also to more soluble ligand field effects, which involve 5f orbital to a greater extent than the 4f orbitals are involved in bonding in the lanthanide complexes. An equation used for calculation of molar susceptibility xi m is given by xi m equal to ng square beta square j plus 1 over 3 kt plus n alpha, where n is Avogadro's number, g is Landis splitting factor, which is given by g equal to 1 plus s plus 1 j plus 1 minus l minus 1 over 2j plus 1, where beta equal to Bohr magnetron, whose value is 9.27 into 10 raised to minus 21 erg per Gauss. Okay, these are comparisons, and then there is this complex formation: singly charged anions, doubly charged anions, And yeah, so now going forward, what sir has taught in the week 11 and 12 classes, let's have a look. So he taught about the application of absorbance spectra, qualitative, quantitative, studying complexation of metal ions, metal ligand titrations, and detection and estimation of the lanthanide and actinide ions in the environmental samples. So there are certain important bands of actinide ions and their molar extinction coefficients. And then there is a luminescent spectroscopy. Some basic terminologies that we have to know is uh, absorption spectrum measures wavelength at which a molecule absorbs light. Excitation spectrum determines the wavelength of light necessary to produce emission or fluorescence from the molecule. Emission of electromagnetic radiation and excitation by an external source. Luminescence is a phenomenon uh, of emission of light in a visible region, fluorescence for a very short period after excitation, and phosphorescence for a relatively long period. We know this, intersystem crossing and intercrossing and their lifetime, radiative transition and non-radiative transition, and then how these vibrational levels are there. So this ground state and excited. So the instrument used is a fluorimeter, and the luminescence can be of different types, different based on the excitation. And the excitation source can be an electron beam, which shows cathodoluminescence, X-ray, gamma ray or particle, radioluminescence, strong electric field, which is electroluminescence, mechanical agitation, which is cryoluminescence or mechanoluminescence, chemical reaction, which is chemiluminescence, and heat source, which is thermoluminescence. Then comes the time resolved photoluminescence or fluorescence. Fluorescence plus phosphorescence giving photoluminescence. And this is the PL lifetime where we get the TRPL spectra. It can provide us about the triple resolution, excitation, emission, high SN ratio, and non-invasive and non-destructive techniques. So the lifetime of a particular species is the time taken for the excited state population to become 1 by E of its initial state. Going further, sir talked about how most of the actinides ions possess energy level that provide ladder-like pathway for excitation energy to dissipate by a non-radiative mode. And then EU3 luminescence, every configuration has its own energy, means 3003 microstates has 3003 energy states. Some of them make degenerate E set also. 3003 microstate, which one is a ground state? The ground state electronic configuration can be understood by using term symbol, a symbolic representation of energy, angular momentum, and spin multiplicity of an atom. Term symbol representation is 2s plus 1 Lj, spin multiplicity is 2s plus 1, s equal to s1 plus s2 dot 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 sn for n electron, and j equal to l plus s2 n minus s. Terms are denoted by capital letters. S for S, L equal to 0, P, L equal to 1, D, L equal to 2, F, L equal to 3, G, L equal to 4, and H is L equal to 5. So S is a total spin and quantum number. And L is a total orbital angular quantum number. Few term symbols for F6 configuration are 7F, 5D, 5P, 5Z, 3L, etc. What about the J value? Since we know L and S, we can easily calculate J value, that of J equal to L plus S to L minus S. Example for 7F term, L equal to 3 and S equal to 3, S 2S plus 1 equal to 7. So J equal to 6, 5, 4, 3, 2, 1, 0. Hence complete term symbol is 7F0, 7F1, 7F2 to 7F6, or 7Fj, where J is equals to 1 to 6. Now how to record in excitation and emission or lifetime spectra? For experimental excitation, emission and lifetime is recorded by fixing the excitation wavelength while the detection wavelength of the spectrophlorimeter is scanned. Excitation source is giving excitation monochromator, and then there is a sample holder, slits are there, emission monochromator is there, then there is a detector assembly. EU3 luminescence is a convention to describe a transition between two 2s plus L1J levels to write the high energy state at the left hand side and the low energy state at the right hand side. The arrow points from the initial to the final state. The instance, the transition from 5D0 state to the 7F1 state in the luminescent spectrum is written as 5D0 to 7F1. The same convention is used for the absorption spectra. The transition from the 7F1 state to 5-0 state is written as this, not this. Okay, you have to remember this. Okay, going further, plotting a spectra wave number or wavelength scale mu bar in centimeter inverses tends to about 7 per nanometer. It is recommended to plot a spectrum in a wave number scale with the highest wave number at the left and the lowest at the right side of the spectrum. Now, EU3 luminescence, the distance between a J and a J plus 1 line increases with increasing J value. That of the 5D0 to 7F1 transition is very close to the 5D0 7F0 transition, but the 5D0 7F6 transition is lying more than 50 nanometer further to the infrared than the 5D0 7F5 transition. Lambda interval value is the interval between the successive energy levels is proportional to the large of the total angular momentum values J. That of the splitting increases with increasing J value. The majority of the transition observed in the luminescent spectrum are induced electric dipole transitions arising from the interaction of the lanthanide ion with the electric field, the vector through an electric dipole. Now, intra-configurational electric dipole moment, example SS, PP, DD or FF transitions are forbidden by Laporte selection rule. Now, magnetic dipole transitions are allowed by the Laporte selection rule, but their intensities are weak and comparable to those of the induced electric dipole transition. MD transitions are largely independent of the environment and can be considered to be constant, which is known as the internal difference. Now, various transitions observed in the EU3 emission spectrum is 5D0 to 7F0, which is electric dipole, range is 570 to 585. 5D0 to 7F1 is a magnetic dipole, 585 to 600. 5D0 to 7F2 is the electric dipole, 610 to 630. 5D0 to 7F3 is electric dipole, 640 to 660. 5D0 to 7F4 is electric dipole, 680 to 710. And 5D0 to 7F5 is electric dipole, 740 to 770. Now, selection rules for various type of transition is for electric dipole, delta S should be 0, delta L should be less than equal to 1, delta J should be less than equal to 1. So, induced electric dipole, which is jet force, where there is no change of parity, and then there is a magnetic dipole. So, all these things have to be remembered. Then EU3 luminescence is application is like complexing of metal ions with different ligands, metal ligands titration to find stability constant, detection of the lanthanide and actinide ion in the environmental samples. Now, emission spectrum can be used to tell the symmetry around EU3 plus in the complex. An important parameter that can be derived from the emission spectra is the asymmetry ratio. It is the ratio of the 5D0 to 7F2 transition peak area to 5D0 to 7F1 transition peak area, and this greater than 1 for asymmetric system. Now, number of emission peak recorded at low temperature. Symmetric system gives less peaks, unsymmetric systems give more peaks. ABC shows luminescence spectra of EU3 plus in different ligand environment. Typical emission spectrum of EU3 plus. Now, the crystal field perturbation destroys the spherical symmetry of the free ion and the 2s plus 1 Lj terms is split up in a number of crystal field levels. The extent to which the 2j plus 1 degeneracy of a 2s plus 1 Lj term is removed depends on the symmetry class and not on the point group itself. For all point groups with a symmetry class, the splitting of a j term is identical. For instance, the splitting of the 2s plus 1 Lj term is same for all tetrahedral groups. The differences between the different point groups are reflected in different selection rules or in different number of transitions that are allowed between two 2s plus 1 Lj terms. Lowering in symmetry results in relaxation of selection rules and to an increase in the number of allowed transitions. For the point group C1, no transitions are forbidden by the selection rules, and transitions are allowed within all the crystal field sub-levels of two 2s plus 1 Lj terms. EU3 luminescence, again talking about it, number of emission peaks recorded at low temperatures. Symmetric system have less peaks and unsymmetric system has more peaks because of the splitting, and this is how you know. Absorption spectrum shows attenuation of incident light by all interband transitions that occur at that wavelength. and decay time or lifetime of a particular species is the time taken for the excited state population to become 1 by E of the initial state. So tau observed lifetime values in millisecond, and the number of molecules in the primary coordination sphere of a metal ion can be calculated from the observed lifetime values by the following empirical relations. K observed is equal to 1 by T in millisecond inverse. Okay, how to record excitation, emission or lifetime spectra? Excitation source, excitation monochromator, sample holder, emission monochromator, and detector assembly. Emission spectrum is recorded by fixing the excitation wavelength while the detection wavelength of the spectrophotometer is scanned, and photoluminescence is there, and then all this about EU3 plus. Now then there is redox potential or redox chemistry of EU3 plus, how you do the separation, estimation, and the chemistry of different oxidation state. We know ln k is equals to n E naught F by RT, P E naught equal to 1 by n log K, and P E equal to P E naught plus 1 by n log oxidation raised to A over reduction raised to B. Okay, we know redox potential of actinides for actinium 3 to 0, thorium 4 to 3 and 4 to 0, and uranium 6 to 5, 6 to 4, 6 to 3, and then plutonium, neptunium, americium, and then you can see starch blue color EDTA colorless solution. How do you control the redox potential? Then they're talking about the plutonium, and then how do you separate? So the separation of actinides in the nuclear industry can be done by precipitation, solvent extraction, and ion exchange. So precipitation is like this method was first used for the separation of plutonium in Manhattan project, and plutonium 4 is co-precipitated along with bismuth phosphate. Now solvent extraction is the most commonly used method in nuclear industry, both in front as well as back end. For metal ion extraction, one needs to an extractant and a diluent. Solvent extraction is principle is at a given condition the distribution of any species in the two phases is constant, which is as per the Nernst distribution law, and D equal to M organic over M aqueous, which is mixed two phases and settle down. Extraction of the metal ion depends on ligand concentration, metal ion concentration, aqueous phase acidity, etc. And requirement is neutralization of metal ion charge by extractant or complexing an ion to make the species hydrophobic, and extracting properties, it is insoluble in water, freely soluble in organic solvent, it should form a reversible complex with metal ions. Faster complexation kinetics, should have a lesser stability, ease of availability, and low cost. And diluent properties like it is non-polar, low aqueous solubility, easy phase separation, low viscosity. Actinide ion extraction by solvation can be done by this method, and you can see here comparison of uranium extraction with 0.1 molar phosphate, phosphonate, phosphonate, and phosphine oxide in kerosene. Now actinide ion concentration by TBP, trivalent actinide ion extracted from HCl medium. Ion pair extraction is the MX process of uranium extraction in the front end of nuclear fuel cycle can be done by this method. Okay, then metal ion extraction by ion exchange, importance of beta diketone ligand in the solvent extraction. Example, there is a ketone in all form. Now TTA is widely used to extract tri and tetra and hexavalent actinides by suitable tuning of aqueous pH. At 1 molar HNO3 pH equal to 0, it extracts only plutonium 4. At pH equal to 2, it will extract plutonium 6. At pH greater than 4, it extracts plutonium 3. Now dissociation of OH group in the enol will depend on the pKa values of the beta diketones. By substituting the R group, pKa values can be tuned. Thus the selectivity for tri, tetra, and hexavalent cations. Example, acetyl acetone pKa is 8.8, phenyl trifluoroacetone, which is pKa 6.2. Now reprocessing of the spent fuel is done by the Purex process, where plutonium uranium reduction extraction process is done. Extractant is 30% TBP and dodecane. Supply and cost, good physical properties, reasonable stability, non-toxic nature, adequate selectivity in fast kinetics. Separation scheme is co-extraction of plutonium 4 and uranium 6, partition of plutonium 3 and uranium 6 and uranium 4. Scheme of Purex process is there is a spent fuel, then there is a dissolution and feed adjustment by 3 molar HNO3, adjustment of valency by 30% TBP, organic phase uranium and plutonium, aqueous phase waste, then there is the organic phase U plus 4 and UO2 2 plus aqueous phase. U and PU recovery and decontamination from fission and activation products is necessary. Comparative extraction of plus 4 and plus 6 actinized by TBP is UO2 2 plus, then PU4 plus, then NPO2 2 plus, then NP4 plus, then PuO2 2 plus, and TH4 plus. And yeah, Purex process advantages is complete process being used for last several decades, cheap and easily available. Degradation products can be washed away. Decontamination factor of FPs are large. Disadvantages is aqueous solubility of TBP, which is 0.4 gram per liter. Generation of solid base, difficulty in plutonium loading, third phase formation, which is impurex. Alternative extractants TIAP, DHOA, variation of DU with acidity, which is 25 degrees centigrade, variation of DPU with acidity, which is 25 degrees centigrade, extractant 1.1 molar TBP, DHOA, and dodecane. So the ion exchange separation of actinides is uptake by cation exchangers MO2 plus, M2 plus, MO22 plus, M3 plus, and then M4 plus. Affinity difference is large with a 6, so separation is easily possible. 6 resin is used extensively and used for intra-group separation by using a selective OH-COH eluting agent, and then other things are there. The Thorex process is there, where this separation of thorium, Pa, and U in short cooled fuels is done, and then TH232 in long cooled fuels, and flow sheet is similar to Furex. So there is a nuclear fuel cycle, there is mining and milling, and there is enrichment, and then there is fuel fabrication. In the nuclear fuel cycle, you have a reactor which reprocess, reposit, and then you do the waste management. You can do the actinide partitioning by using ligands like CMPO, DMD, BTD, MA, TRPO, TODGA, etc. So talking about the Truex process, the extractants is octyl phenyl N or N diisobutyl carbamoyl methyl phosphine oxide 0.2 molar. The phase modifier is TBP 1.2 to 1.4 molar. Diluent is paraffinic hydrocarbon. Extraction train is Pu plus 4 is highest, then UO2 2 plus, then AM3 plus, and used for the separation of trivalent lanthanides and actinides, as well as known as SETFIX. SETFIX full form is solvents extraction of trivalent F block elements intra-group separation in CMPO complexant system. The complexing agent we use are DTP or NaNO3, and it is used for the selective stripping of AN3. Disadvantages are they are P-based extraction and they have stripping issues. Then there is TRPO process, DIDPA process, and Dimex process. Read about it. Toja process. Why Allen and AN separation? Allens have a very large end absorption cross sections. From separate phase during vitrification, separation can be decreased the waste volume significantly. The AN3 can be used for transmutation of heterogeneous recycling. Now the process for Allen AN separation is Tremex, Talspeak, Cruisepeak, reverse Talspeak, LSEP, amino polycarboxylate. Senex 1, 2, 3, which is aromatic heteropolycyclic, Senex 4, which is dithiophosphonates, Ganex, Uroganex, which is aromatic heteropolycyclic, R-Senex, 1C Senex, aromatic heteropolycyclic, I-Senex, aromatic heteropolycyclic, which is aqueous soluble. Now then there is soft donor ligands, Terpi, BAT-PTZ, and then I-Senex, RBTP. The limitation is poor solubility in suitable organic diluent soluble in 1-octanol. Innovative Senex process with aqueous soluble BTP ligand, and then AMCM separation decreases waste lifetime, and radiotoxicity decreases long-term waste heat power and saves repository resources. Strategy is to separate AM and opt for heterogeneous recycling, U plus PU plus AM. Strategy is separation using specially designed complexing agents such as TRAPEN, and selective oxidation of AM to the plus 6 state followed by TBP extraction. Unusual oxidation state is this, and then unusual oxidation state of thorium, and americium, then analytical chemistry, gravimetry, spectrophotometry, their applications, and the natural origin. Now, in the environment, how much are there, and migration of plutonium in the groundwater at the Nevada test site, and an actinide in the environment, oxidation state, hydrolysis, colloid formation, absorption, and filtration effects. Now, the most important is the speciation. Speciation may be defined as a determination of the various chemical and physical forms of the element under investigation, such as its oxidation state, all possible inorganic or organic complexes, precipitation, etc. Now, direct non-invasive spectroscopic techniques are best studies for speciation analysis. The techniques are EXAPS, ZINS, XPS, SEM, and TRLFS. So the combination of these techniques helps in better understanding of surface and aqueous speciation of actinides. Now, why to study speciation? As we know that the presence of actinide in our food chain is harmful because of the associated radiotoxicity and chemical toxicity of the actinides. The chemical properties of such as solubility, mobility, bioavailability, and in fact toxicity of the actinides are governed by its separation under a given set of chemical conditions, and a thorough knowledge of speciation is required to prevent or minimize the bioavailability of actinides. The speciation of actinides decides solubility, mobility, bioavailability, and toxicity. Factors deciding speciation is this: speciation diagram of NP5 as a function of pH. The predominance of NP as NPO2 plus can be seen up to pH 9. Later hydrolysis starts. For Beck's diagram, PE-pH stability field diagram show in a comprehensive way how protons and electrons simultaneously shift equilibria of reactions under various conditions: area lines, horizontal lines, vertical lines, and the slope, etc. Humic acid actinide complexation, proposed structure, and why to study absorption and migration behavior. This is an application part of whatever you have learned till now of actinide speciation. In any unfortunate scenario, if there is some leak of radionuclides in the environment, the first thing is encounter of the soil, which is basically composed of clay minerals and a complex assemblage of different oxides in different proportions. The movement of radionuclide to the clay oxide can lead to interaction with wind. To that interaction we need to study, and this will help in understanding of the migration or the movement of the radionuclides from place to another. This information is essential in many aspects, such as to avoid the radionuclide from becoming the part of our food chain, choosing better buffer backfill material for the deep geological repository, remediation of any radioactive contaminated sites, etc. Now, before going to see the interaction between the radionuclide and the clay oxide surface, let's see some properties of oxide clay surface in aqueous media. The surface of oxide clay has surface OH group, or more correctly hydrated hydroxyl group. The clay also have surface hydroxyl groups like oxide, but in addition to the oxide, clay minerals have a sheet like structure and are composed of mainly tetrahedrally arranged silicate and octahedrally arranged aluminate groups. Depending upon the arrangement of silica and aluminates, clay can be divided in several groups such as smectite, kaolinite, etc. So it is a tetrahedron unit, it is an octahedron unit. The fundamental units of a tetrahedral sheaths and octahedral sheaths can combine with the hydroxyl group. Different combination of these units and chemical modification of the basic structure giving rise to the range of clay minerals with different properties. Now, types of charge in clay is permanent charge due to the isomorphous substitution, the replacement of one ion or another of similar size within the crystalline structure of the clay. Al3 plus by Mg2 plus in octahedral sheet, Si4 plus by Al3 plus in tetrahedral sheets. Due to isomorphous substitution, neutral octahedral sheet net negatively charged. Variable charge due to adsorbed ion charge, pH dependent charge. As the name suggests, the pH dependent charge varies with the pH of the medium. Generally in acidic pH range, the surface hydroxyl groups are protonated and surface charge is positive, whereas in alkaline pH range the surface hydroxyl group are deprotonated and surface charge is negative. point of zero charge, the pH at which the surface charge is zero varies from one clay to other. For the isoelectric point, the suspension pH at which the surface at a net zero charge is known as the point of zero charge. If pH is less than pH C, the surface is positively net charged. If pH is greater than pH C, the surface is negatively net charged. So specific surface area is meter square per gram. Clay concentration is gram per liter. Surface concentration is mole per gram. Surface density is mole per meter square. Some conversions are surface concentration over specific surface area, surface concentration over clay concentration, surface concentration cross Faraday constant over specific surface area. Now, how to measure a surface charge potential, zeta potential, and these certain characteristics, can go through them. And then there is a mechanism and nature of complexation, possible interaction absorption mechanism, which is ion exchange, surface complexation, nature of the complex, inner sphere, partial or no hydration sphere, outer sphere with hydration sphere. And in the inner sphere complex, the hydrated metal ion shuts its primary hydration sphere and attached to the mineral surface by largely covalent bond, whereas in the outer sphere complexation, the metal ion retains its primary hydration sphere and approaches electrostatically to a critical distance. Spectroscopic techniques to identify the nature of surface complex is EXEFS or TRLFS. And then uptake of urium-6 by goethite or kaolinite, and then effect of humic acids onto absorption of trivalent lintonites, etc. Now, colloidal transport of actinide, intrinsic or real colloids, pseudocolloids, factors that affect the colloid stability, and then formation of colloids and their studies. Colloids and the transport of radionuclides, contaminants transport in a two-phase system, contaminant transport in a three-phase system, transactinides, position of transactinide, properties, challenges and experiments. Synthesis of only few atoms are there, production and detection rate, atoms are at a time chemistry, very short half-lives. Requirements are fast transport and separation system, online detection system of high efficiency and resolution. These challenges can only be met with highly sophisticated automated instrumentation. Super heavy elements like Lr 254, 55, 69, 60, 61, 62, 64, 66. The half-life is varying from 13 seconds to 10 hours. On the basis of transactinides, it should have lower half-lives. The island of stability was predicted in 80s at Z equal to 114 and N equal to 184. Subsequent theoretical calculation have suggested that N equal to 162 is more likely and Z equal to 126 or maybe 120 may give the more stable nuclides. Synthesis of transactinides is this. Heavy elements beyond FMZ100 are done by fusion reaction, cold fusion, hot fusion. Experimental setup, atom at a time chemistry, relativistic effect, direct, indirect, spin orbit splitting. Now chemistry of 104, 5 and 6, halides, oxyhalides, thermochromatography, isothermal gas chromatography, online gas chemistry apparatus, ARCA, CSEC for rapid separation, aqueous chemistry of Rutherfordium, ion exchange strategy of Rutherfordium, CSEC experiment of 104, aqueous chemistry of dubnium, and then the chemistry of seaborgium. Seaborgium is a member of 6 group, like molybdenum, tungsten. Most stable isotope is 269 Sd with a half-life of 14 minutes. From cation exchange column eluted with 0.1 molar HNO3, 0.15 millimolar HF together with MoO42 minus and WO42 minus, shows very similar properties with group 6 element but does not show uranium like properties. +5 and +6 oxidational state, +3 state is strongly reducing. As one descend in the group, lower oxidation state become unstable. Elution of tungsten tracer modeling the seaborgium, separation on ARCA, and the molarity is 0.1 molar HNO3 plus 0.0005 molar HF. Okay, so this is what sir has taught in the lecture 11 and lecture 12. So now let's begin with the assignment. These are the 25 questions based on the classes of lecture 11 and lecture 12. So let's start without delay. The first question is saying which is the most probable species of the uranyl ion present in the alkaline carbonate solution. So option A is 2 minus, option B is 4 minus, option C is UO2 CO3 2 minus, or option 4 is UO2 CO3 4 6 minus. and we know it very well that for this the oxidation of state of uranium has to be seen, and the one which is having the most probable uranyl ion which is profound will be the right answer, and the right answer is option number B. Now for the reduction reaction NpO2 plus 4H plus electron giving Np4 plus 2H2O, we will get dash in an EHPH plot. It should be horizontal line, vertical line, slant line, no line. We know it is a slant line. Question number 3 is saying the inertness of hydroxopolymer of tetravalent actinide dash with dash relative percent of oxo and hydroxo bridging. The answer is increases with increasing and decreases with decreasing. It's a MSQ, and the right answers are to increase increasing, decrease decreasing. The primary hydration number of Ln decrease with increasing atomic number, but total hydration number goes up to due to dash and dash respectively. The answer are decreasing size and high surface potential. Next question is the hydration of lanthanides are entropically dash and enthalpically dash. So entropically they are unfavorable, but enthalpically they are favorable. The oxidizing tendency of the medium dash with dash Pe of the medium, increase with increasing and decrease with decreasing. The slope of oxidizing and reducing boundary condition of water in an EHPH diagram are dash and dash respectively, -1 and -1. Calculate the Pe naught for the reduction of Pu4 to Pu3. The standard electrode potential for the Pu plus 4 plus electron is giving Pu3 plus, it is 1.017 volt. So the accepted answer is 17.24. The FF absorption transition with delta S equal to 0 are dash compared to delta S equal to 1 transition more intense and allowed. The reduction of Pu4 to Pu3 in acidic media can be achieved by hydroxylamine hydrochloride. For recording the triboluminescence we use what? Mechanical agitation, we know it. The transition from the 7F1 state to the 5D0 state should be written as 7F1 to 5D0. The lifetime of a particular species in the time taken for excited state population to become dash of its initial population, it should be 2.72 inverse. We know it very well. The extraction efficiency of phosphorus based ligands are given as, first one is phosphine oxides, then phosphinates, then phosphonates, and then phosphates. The F element with configuration Fn n equal to greater than 0 can give absorption spectra due to both A and B, interconfigurational transition and intraconfigurational transition. What are the species extracted in 1.1 molar TBP and dodecane for U6 and Pu4 from 3 to 4 molar HNO3? It is UO2NO3 whole twice dot 2 TBP and PuNO3 whole 4 dot 2 TBP. Which of the following are referring to amine based extraction of actinides? MX and TREMX process. The Purex process uses dash as a solvent, 30% TBP. Which extractant is used for extraction by a solvation mechanism? Diethyl ether. Which of the following reasons are not used for uranium estimation at micromolar concentration? Thiocyanate. Which of the following reagent is used for adjustment of oxidation state of Pu3 as well as Pu6 to Pu4? The answer is nitrite. Which of the following is not an extractant used for actinide partitioning? TBP. The separation of an AM and CM can be done by the following processes. CSAM. Which is the correct combination of LNAN separation? Sulfonated BTP and Isonex. The online chromatography system or transactinase is called as ARCA. Which are the homologs of rutherfordium, zirconium and hafnium? Which one of the following is used as pacemakers? Pu238, we know it. Autoradiolysis is mainly due to the radionuclide output of which of the following isotopes of plutonium is 238. HFIR stands for high flux isotope reactor. The last two questions are, what should be the general order of absorption of U6, Pu4, AM3 and NP5 onto a given oxide surface? The order is Pu4, then U6, then AM3 and then NP5. Which of the following set of orbitals get contracted and expanded respectively by relativistic effect? S and P and D and F. So thank you, this is all. I wish you very best for the exam, and before the exam still if you have any kind of doubt, please feel free to WhatsApp and email me. I hope I have answered all your queries, All the best for the exam, and see you. Good learning. And you always have my number. If you have any issue, you can contact me.